Hi, Dr. Cook here. This lesson we're going to be talking about stability. Right, now, stability is a really critical factor when we're looking at aerodynamic performance of a projectile. Right now, the drag, which is one of the largest forces acting on our projectiles, is dependent on the orientation relative to the velocity vector. Right, so if we have rapidly changing orientations because we're unstable, that's going to make it really difficult to determine what's going on with the drag and the velocity and then where the round is even going. Okay, so that's why stability becomes very important, so we can predict our flight paths accurately. All right, and inability to accurately predict a flight path due to an unstable projectile is just dangerous to friendly troops and civilians. All right, in order to do this analysis, we are going to use linearized aeroballistics. Okay, now what that means is that we are assuming a linear relationship of our forces and moments to the angle of attack. All right, and we can do that through this equation 10.1, looking at both our force for any one of them, lift, drag, whatever, as being proportional to that coefficient times the sine of our yaw angle, or for the moments, whatever coefficient we're looking at multiplied by our diameter times the sine of our yaw angle. All right, now why do we do this? Okay, one thing is that it simplifies the math a lot by doing that. And it helps us determine the quantities of interest quickly. Okay, what parameters are the most important ones that a designer can change to affect our flight characteristics? Okay, so it gives an easier math way to do that. It helps us out with how we can do parameter sweeps, all right, when we're running our designs, or if we need to do concept assessments very quickly, almost on the border, what we might call that back of the envelope calculation, where we've got a concept, we've got an idea, we just kind of need a quick answer, all right? We can understand how the effects are going to change in all of our forces by making the changes this way, because it's just a linear model, much simpler than a full 6-degree of freedom one. All right, now we're going to start out by just defining some terms mathematically that we're going to use in our equations later. The first one here, we've got a reference area for our projectile based on its diameter. Now, we also are going to start introducing these starred coefficients. Okay, now in here, the J is just a stand-in for whichever particular coefficient we're looking at, right? So, C sub D, then C star sub D, or C sub L, C star sub L, right? So the starred version just captures these other parts here where we're taking into account, density, reference area, diameter, and mass, okay, to create a starred coefficient. All right, then we have this K coefficient, K sub T, which we are going to use later based on our momentums there, right, our angular momentums. Now, for a spinning projectile, all right, so the following coefficients are only used for spinning projectiles, all right? So we have a coefficient called H that we're going to be reusing, all right, that is based on, a number of our different coefficients, all right, and that is 10.77, all right? So you can see, then we have a coefficient that's called T, all right? So a transverse coefficient is kind of what some of this stuff captures here. And then our final one, G, which kind of captures some of our gravity term here. So these are just coefficients that are used in the equations later, all right? Okay, now, the big concept here for stability is understanding epicyclic frequencies. All right, what does that mean? All right, so I've drawn a little coordinate system here. All right, so let's just say that we've got pitch, which is alpha, shown here on the y-axis, and we've got a beta axis for the yaw. All right, it's an imaginary number for the beta here. All right, And what we've got is that our flight path is the center of this. So this is essentially, we are behind the projectile looking forward in the direction that it's moving, okay? And our flight path, our velocity vector, is located at the origin of this graph here. So that's the reference frame of this picture, all right? Now, from the velocity vector, all right, we're always going to have this yaw of repose. All right, so that's kind of that constant, little bit of tip in the angle there where it's yawing off to the side. Now, I know that we've used other variables before, but now we're introducing this new variable to represent our yaw of repose, just keeping with the kind of standards in working with this kind of linearized aeroballistics. All right, so first we've got to move off for our yaw of repose to get to the actual nose of our projectile. Now from there, then we've got these two arms, all right, that stick out, okay? And we label those as K1 and K2, all right? So sometimes they're referred to as a long arm and a short arm, or a fast arm and a slow arm, all right? But we've got a K1 fast and a K2 slow that stick out from that, all right? And those vectors all combined together is where the nose will actually be at this moment in time, all right? So all the way up there at the tip of the yellow arrow, at the tip of K1 is where our nose actually is located while our vector is taking us towards the origin here. All right. Now, if we look at that K1 arm, all right, we can draw just a little dotted line here that's parallel to the yaw axis. All right, and there is some angle there. So at this moment in time, we've got this angle off of the yaw axis that it's sitting at, all right? And we've got another angle for the other arm, all right? Because these two things move, all right? And they cycle around. So K2 is making a circle around where the yaw of repose puts us at, all right? And while that is happening at the very same time, so remember, K1 is attached to the end of K2, right? So the base of K1 is always moving around that circle along with K2, except that it's spinning also. All right, so K2 is, K1 is spinning while it is moving around the end of K2 that is spinning around our yaw of repose, which is a constant offset, right? And that's going to create kind of that spiral graph kind of idea of just where the nose is just wobbling all over the place, all right, while this is happening. All right, and this is figure 10.7 out of the text. All right, now those angles for both the arms 1 and 2, the fast arm and the slow arm. All right, what that angle is, all right, is defined by this equation here: 1/2 of p plus or minus the square root of p squared minus 4m. All right, 10.85, and notice there's a plus or minus there. All right, so that's how we end up with two answers coming out of this equation here, right? This is our change in the angle, all right? Now, these are called the nutational and precessional rates, okay? Because notice the little, these are marked off as a rate, not the actual angle, right? It's the first derivative. Now, number 1 here is called fast, that's the nutational part, and number 2 is the slow arm, that's the precessional part, okay? Now, how do we define these P's and M's? All right, so P, all right, is given here in equation 10.81, which has to do with the polar momentum divided by our transverse momentum multiplied by our density times our diameter divided by the velocity. All right, and then our M portion is 1 over that KT squared coefficient multiplied by our starred coefficient of the overturning moment, right? And that is 10.78. All right. So once we know those, we can calculate how fast these two things are moving around to drive our nose in different places. Okay, now this is figure 10.4 from McCoy's Modern Exterior Ballistics. I just thought it was a good figure to show you to kind of illustrate this. So we've got that same yaw and pitch axis here kind of shown on the plane along with the projectile to give you an idea of, all right, the velocity vector is going through that coordinate system, but where's the nose pointing and how it traces out, you know, this epicyclic motion is shown there as we have the fast and slow arms rotating around each other there to kind of illustrate those and how that works out. Okay, now how do we use these to figure out our stability criteria? Are we stable or not? Now, on this slide, we're going to talk about for spinning projectiles. All right, this does not the criteria for non-spinning fin stability projectiles. For spinning projectiles, all right, we don't need an imaginary part. All right, so we can say that if p squared minus 4m is greater than 0, we are stable. All right. Now, we do a little math to that. We figure out if p squared is greater than 4 times m, we are stable, which means we can say we are statically stable if m is less than 0. All right. Now, this other quantity of the whole thing being greater than 0 still holds, but anytime m is less than 0, we have to be statically stable, right? Because our p squared term will always be greater than that, right? Now, we also have something called gyroscopic stability, all right? And our gyroscopic stability factor, S sub g, is equal to that p term squared divided by 4m. That comes from 1099, right? And we are stable if that S sub g value is greater than 1. Now, I want to make a comment here that anytime we are statically stable, right? If we're statically stable, we must be gyroscopically stable, okay? And if we're not statically stable, we would be gyroscopically stable if S sub g is greater than 1. We also have a dynamic stability factor, right? That is S sub d equal to 2 times that t coefficient divided by the h coefficient, equation 10-100. All right, and for that, we are dynamically stable if all right, our dynamic stability factor multiplied by the gyroscopic stability factor multiplied by a quantity of 2 minus the dynamic stability factor, all of that is greater than 1. Then we will be dynamically stable. Okay, so next we're going to talk about the yaw of repose and roll resonance. Okay, so let's start with the yaw of repose. Now, we introduced that in the past about what the concept of it was. Now, in this kind of analysis, we are using a unitless value for the yaw of repose. Now, that subscript g represents the fact that the yaw of repose comes about because of gravity acting on the projectile, okay? And we can use 10.109 to get our unitless yaw of repose value out of this. Now, if we analyze this expression, some interesting things come out of it, all right? One is we have to realize that the spin rate affects the amount of yaw. All right, so as our spin rate increases, okay, then the greater the yaw of repose is going to be. All right. Trajectory is also affects our yaw. All right, and our maximum yaw happens at our maximum ordinate. All right. Okay, so next let's talk about roll resonance. All right. Now, everything up till now, we keep making this assumption that our projectile is completely axial symmetric. All right. Now, reality is we don't have good enough manufacturing to do that. Right. There's going to be some little bit of variation, and something's going to be off axis in our center of gravity, center of pressure, our dimensions, whatever. Especially when we start putting fins on the back of something and they might not line up quite right or have different dimensions or whatever, right? So we end up with this potential for roll to happen and a roll resonance frequency as we interact with the air, right? Now, this is something that's much more common in fin stabilized projectiles, all right, because we're adding those extra forces onto the sides. All right, a slight asymmetry, all right, can cause an angle of attack change, all right, on our projectile. Our roll rate, when that gets close to one of these epicyclic frequencies coming from those long and short arms, we can run into a resonance problem. Okay. and that will cause us to tumble out of control, right? Because once that starts to get near that frequency and it resonates, then we get massive changes in our angle of attack, and we lose control of our projectile flying through the air. All right, so in this presentation, we talked about some of these ideas of dealing with stability, what our epicyclic frequencies are in those fast and slow arms. We talked about the impacts of yaw of repose and what our stability criteria are. All right, so understanding those stability criteria so that you can evaluate a scenario and figure out if a projectile is going to be stable or it's going to be unstable, we're going to lose control out of it. All right, have a great night and see you in class.